atom, here's what we need to understand. The central part of an atom, okay, is known as the nucleus. So when I look at an atom, this middle portion right here is called the nucleus. Okay? The nucleus is made up of things called protons. This is one of our pieces that make everything up. Okay, those are represented by the green beads. And then neutrons. Okay? The thing about protons you need to understand is that they are positively charged. Okay? Protons are positive. Okay? And then the other part, like Mitchell said, is there's also neutrons in there. But they are neutral. They don't have a charge. Okay? So we have protons and neutrons inside the nucleus. And then the other part of an atom is everything that's outside the nucleus, and that's where the electrons dwell. Okay? And they are negatively charged. Okay? All right, so let's make some connections here. So you're going to draw some arrows on your little chart to connect some things. Okay? So the first thing you need to understand is that the weight of an atom, the mass of an atom, is really all about the protons and the neutrons. Okay? So protons and neutrons make up the atom's mass. Okay? You might want to write those arrows in, connect those two together. Okay? Another thing, so do you guys see that big black box on the top of your notes?
Oh.
So that was supposed to be that. I didn't think about it when it printed. So redraw this box maybe over here, because we need that. So redraw your nitrogen square up top somewhere. Doesn't really matter where, but you're going to need that. So redraw a nitrogen square here. Because what we want to do is we want to make a connection of when I look at the periodic table, what it tells me. Okay? So draw that in, and then we're going to make some connections here. So the periodic table today is your answer key, but you need to know how to interpret it. Okay? Yes. So the first connection I want you to make is draw an arrow, ready? From atomic number up to that 7. Okay, so when you look at the periodic table, the atomic number is that number 7 up there. For nitrogen, at least. And that is equal to the number of protons. Okay, so when you look on the periodic table, you know how many protons an atom has. Something that's key to recognize about a proton is if you change the number of protons, you change what it is. If it has 7 protons, it's nitrogen. If it's nitrogen, it has 7. That can never be different. These ones can. Neutrons and electrons can change for nitrogen, and it's still nitrogen. But if the proton number changes, it changes what it is. And that's going to be key as we learn about how they made brand new elements. Yeah, Jason?
Is no two elements have the same protons?
Good. Yeah, no two elements can have the same number of protons. Yeah, no, that's perfect. Okay, another connection here is there's a box that says this. Equal in a neutral atom. Equal are the protons and the electrons. Since protons are positive and electrons are negative. All right, so we're not going to spend a ton of time on this. Okay, all right, if you can't sit by your friends and listen, you can't sit by your friends. Thank you. Okay, so once again, this isn't really our focus. Our focus is on protons, neutrons, and electrons, okay? But it is important to recognize that there's actually more to an atom than those. This is a very new science. It's something that is kind of complicated. So once again, it's not something we talk about in high school chemistry. But I just want you to understand that they are there so that if down the road you learn about them, you don't come back to me and say, you lied. There's more to a proton, because there is. Protons and neutrons are actually made up of something. They used to think that those were the smallest you could get, that you can't split a proton. Well, you can, and they're made of things called quarks.
Quarks?
Yeah.
Like ORK?
What?
Like ORK? Quarks.
Quark is what they decided to call them. So 3 quarks make up a proton or a neutron. There's actually, so total, there's 6 different types of quarks out there. And so protons and neutrons are made in different combinations of those. These are, just fun fact, these are the different names of the quarks that we have. So they're called up, down, charm, strange, top, and bottom, are the different names of the 6 quarks. We need to learn here, which is known as the mass number. Okay, the mass number equals the protons plus the neutrons, which means it has to be a whole number. Because even though protons can be split, they don't exist that way. Right? They exist all together. Okay? This is key. The mass number, everyone, is not what's on the periodic table. Okay, this is going to be your most common mistake you make today, and some of you are going to make it in 3 minutes. I'd place a bet you will. Okay? The mass number is not the number on the periodic table. Okay? We've looked at that number a lot when we've been adding up the masses of the atoms. It's related to it, but it's not exactly it. Okay? We're going to learn where that comes from at the end of the day. What it is the mass number is we have to know what isotope it is. Okay? So, an isotope is atoms that are the same element, but they have a different mass number. Okay, so for example, hydrogen, okay, hydrogen has 3 naturally occurring isotopes, hydrogen 1, hydrogen 2, hydrogen 3. They're all hydrogen. To you, they could all be in this room right now and you wouldn't know the difference, okay? The only difference is their mass. Hydrogen 3 is heavier than hydrogen 1, okay, because of the neutron. The key thing is they're all hydrogen, so their proton number has to be the same. That can't be different. If their neutron number is different from one another. So when we label an isotope or an atom, we have to include that mass number because it could change. So the notation we use is the mass number goes up top, and then the atomic number goes underneath. In my opinion, and you may see this sometimes, it's redundant to put this 6 here when you're telling me it's carbon. Why? Yeah, because carbon's never going to be anything but 6. This number will never change if it's carbon. This number could. There's carbon 12 in your body, and there's carbon 14 in your body. You don't know the difference. Chemically, we don't know the difference. Carbon 14 is a little bit heavier than carbon 12. Okay? So whenever you're talking about an isotope, I thought of this analogy this morning, but it's like wrestling. Because in wrestling, you label the wrestler by their weight. Isotopes, you label them by their weight as well. So you call it carbon 12. You can't just say carbon, because otherwise you don't know what isotope it is.
So if there's more of it, it's gonna be carbon 16 or whatever. So
Yeah.
it depends on how
If
much
it was just a heavier isotope. Yep, exactly.
Do all atoms have isotopes?
Yes, some have more than others. Like some have like 2 different, some have like 5. There's also some man-made isotopes as well.
Where do you figure it out? Will always be given to you?
Yes, so that's what we'll go over here, is we'll have to figure, they have to give you some sort of information, otherwise you wouldn't know. If they just say carbon, you don't know what isotope they're talking about. Okay, so let's walk through this problem together, and then I'll have you try the second one on your own. So everyone follow along with me here, okay? So I'm telling you that it's isotope chlorine 37. So first off, somebody by raise their hand tell me, how do I find the atomic number for this? So that's what I do. Good. Look on your periodic table, find chlorine, everybody. What's its atomic number? 17. So fill that in. Okay, the atomic number just comes from the periodic table. Okay, what is my mass number?
37, because that's how much it weighs.
Good, and where'd you find that, Jace?
Right next to chlorine.
In the name. If you looked on your periodic table, chlorine has 35 under it. That's not the mass number. The mass number's in the isotope's name.
Then why do they give you mass numbers on the periodic table?
So it's close to it, right? See how it's 37 and that's 35? We'll talk about where that one comes from in a second here. Okay, how do I find protons?
Did you split them up between electrons?
What'd you say, James?
It's just 17.
Where'd you get that from?
From the power number?
And will those always be the same?
Yeah.
Yes.
Yes. Atomic number and proton number are always the same. That will never change. Okay, how do I find my number of electrons?
Just put
Jason?
a negative in front of 17 because it's a negative.
Oh, so we know that we said if it's neutral, it's going to be the same. Because we're counting them, you don't actually do a negative, it's just 17.
17 again.
Yep. Because you can't really have negative of something. But what if it wasn't neutral though? So let's say hypothetically, I was looking at now, if I told you that this was chlorine with a -1 charge, how many do I have then, Austin?
18.
How'd you get 18?
Because one more electron is a negative.
Good. So if it's a negative charge, that means you have more electrons than you do protons. If it was positive, then it would be the other way around. But are you ever going to change the proton number?
No.
Because then it wouldn't be chlorine anymore, right? All you're going to change is how many electrons it has. Good. So these are only equal because it's neutral.
Oh, because it's so how do you know if it's not?
In the name,
Okay.
it would maybe show you the charge, or like in the symbol, like here, it showed you the charge.
So if it's copper.
And then how do I find my neutrons here?
17.
So where do I get the neutrons, Holly? Good. So we do the mass number minus the protons. So 20. Okay?
So, on the mass number, 37.
Mm-hmm.
37 what?
So 37 is the mass of the atom. AMUs are the units we use.
So does each proton or electron or neutron weigh one and
Well, the mass number is just protons plus neutrons because electrons are so small, they don't really affect it.
well, so each proton or neutron weighs 1 on
Relatively, yeah. I'll show you in a second here. Like they actually have some decimals, but it's like 1.008 something. So they're really close to just 1. So, yeah. Okay, look at this, everybody. So, if my problem didn't give me the mass number, so it didn't give me that 37, what would it have to give you in order to solve this? There's something that, if they don't give you the mass number, they have to give you something else. What do they have to give you? Good, Aubrey, they'd have to give you the neutrons. Because otherwise, you don't know what isotope it is. You can't not know the neutrons, and you can't know the mass number at the same time, because there's no way of figuring it out.
So how do you work back from the neutrons?
So let's say if I knew this was 20, how would I find the 37?
You just need.
Oh, you add the 17.
Then you just add them. Yep, just do the reverse. Okay, try the next one for me on your own, and then we'll check it here in a second. Oh, sorry, in that little star thing really quick, write the symbol for me. So that's how this symbol would look after you figure out what it is. So write that in the little star. Okay, and then try that practice problem, and we'll check it here for up to 5 smiley faces. Compare your answers to the board and see how you did. You can have 1 smiley face for everyone that matches.
Yes! No way! Yeah. This is how I stack up.
Okay, anyone not match up and you don't know why? I'm going to be honest, on the homework that we work on here in a second, where most people are messing up is the electrons. Okay? So be careful with the electrons. Alright, ready? You can have 1 more smiley face if your symbol matches, but it has to match pretty darn close.
Yes. Oh, what if I just
If you don't have the charge, you can't have it, but if you use Roman numerals instead of the 2, I'll give it to you this time.
What if I just put 2 there?
As long as you thought about the charge, you can have it. But if you didn't think about the charge, no. So the biggest thing is you've got to put the charge in that symbol if it has one.
6 smileys.
Okay? Alright, any questions?
Are we finishing the rest?
Yeah. Okay, last little bit for today, everyone, is now we're going to answer Mitchell's question of that number on the periodic table, where that comes from. Okay? So, all atoms because they're so small, scientists had to develop a new scale for weighing them because a gram's just too big for how small an atom is. So what we have are these things called AMUs, is how we abbreviate them, and they are an atomic mass unit. Okay? What scientists decided is that one atomic mass unit is equal to 1/12 of the mass of a carbon-12 atom. They just decided that carbon-12 would be their standard to develop the rest. So from that, that's how we get the weight of our different subatomic particles. So like we brought up earlier, one proton is approximately 1 AMU. One neutron is about 1 AMU. But one electron, look at this, one electron is 0.0005 AMUs. Okay, electrons are so small in comparison. Okay, a comparison you can make is that to equal the mass of one proton, you would need 1,830 electrons.
Whoa.
That's why electrons moving doesn't change the mass, because they're just teeny tiny. That's the last thing we need to know how to do, so focus back up front. Here we go. So on the periodic table, that number at the bottom is known as the average atomic mass. You can often just call it the atomic mass, but it's not the mass number. What it is it's a weighted average of all the isotopes' mass numbers. Okay? So what we do is we take all the isotopes for that element, and we take a weighted average of them. Can somebody tell me what's a true average? Like, how do I calculate a true average of something? What do I do, Jace?
Do like whatever it is divided by whatever number you're dividing by?
Good. So we like add them all up and then divide by. I knew what he meant.
What average you want? Like, if you want like, what's the average for half the class, and you do the whole class total divided by half the class.
There you go. Yeah. Okay. With an isotope, though, we want it to be weighted towards whatever we have more of. This is how your grade is calculated in this class, because all points are not equal, right? Your grade is calculated by giving more credit to assignment points than the warm-up points, okay? So this is the equation we're going to use. So plug this in, write this into that little box right there. To calculate, this is the last thing you're going to do on your assignment today, to calculate the average atomic mass is you take the mass of each isotope times by their percent abundance, plus the mass of the next isotope times by their percent. However many isotopes you have to do it that many times, and then you'll divide it all by 100.
Why is it always 100?
Because we're basically changing the percents to a decimal. So you can also do a second equation instead, where if instead of dividing by 100, if you just change them to a decimal to begin with, then you don't have to. But that's fine. Okay, so let's try a problem together, similar to the ones you'll see on your assignment. So we want to calculate the average atomic mass of oxygen. So fill this in with me, ready? So to calculate the average atomic mass, we need to take the mass of the isotope, so it's oxygen 16. So 16 is the mass, and we need to times it by the abundance. So 16 times 99.76. Then plus, go to the next isotope, so isotope 17 times that percent abundance, so 0.04, plus 18 times 0.20, and then divide that all by 100. So you take the mass times the percent, add them all up, divide by 100. Okay, ready? Tell me this really quick. Before you even plug anything in, if I were to take a true average, so 16, 17, and 18, if I average those three numbers, what do I get?
17.
17, because it's right in the middle. But now that we're taking a weighted average, which one of these numbers should our answer be closest to?
16.
Why?
Because it's lower.
Because my percent abundance of it is a ton. This would be like if tests were weighted 99% of your grade, right?
Pretty much in my math, it's 80% of my grade.
Pretty high, right? But you should know that whatever has the highest abundance, the answer should be closest to that. The other thing is, where did we say we find the average atomic mass? Where can we look to find it?
Periodic table.
On the periodic table. I'm already telling you the answer. You can find it by looking on your periodic table.
16.00.
So it should be really close to, on the paper it's 15.9994. When you do the math here, you end up with 16.00. Just because of decimal differences. Okay, of it not being a precise mass.
So is your units always AMU?
Yep, always AM. Okay, let's try this one really quick, and then we'll spend the rest of the time on the homework. So if you feel good, you can try this one on your own. If not, you can walk through it with me. So this problem, everyone, is the same idea, but they give us a little bit of different information. Okay? So we're still trying to find the atomic mass. So to find the atomic mass, we need to take the mass of the isotope. So it's chlorine 35. But what's my percent abundance of it?
80%.
How'd you get that?
8 out of 10.
Yeah, so sometimes they may not tell you the percent, but 8 out of 10 means 80%. So I'm just going to show you, you can also, if you want to just plug it in as a decimal, so 80% as a decimal is 0.80.
It's the same.
Right, this is as a decimal. I don't have to divide my answer by 100 anymore, if you do it that way. So either way is fine, this is my preferred method, so then we do plus 37 times 0.2, because that's 20% as a decimal.
Is that 3.5?
Say that again.
No, 3.5.
Oh, this right here?
Oh.
It's 35. And then when you plug it in, say it again. Because it told us that for every 2 out of the 10 is chlorine 37, so 2 out of 10 is 20%. And then when you plug it all in, you get 35.4. Questions on that?